today's algorithm, we're going to be discussing the LeetCode question, path sum. Now, this question asks, given a binary tree and a sum, determine if the tree has a root to leaf path such that adding all the values along that path equals the given sum. Essentially, we want to find a sequence within this tree that is also a root to leaf path that sums to a given integer. Looking at the example on the left side of the screen, we notice that this tree should return true because there is a root to leaf path that equals 22. That path, as we can see, is 5, 4, 11, 2. The sum of 5, 4, 11, 2 is 5 plus 4 is 9, plus 11 is 20, plus 2 is 22, so we're going to return true. What you'll notice here as well is there is another path, 5, 8, 9, that also sums to 22. But if the path 5, 4, 11, 2 did not exist in this tree, we would still not return true here because 5, 8, 9 is not a root to leaf path. That's a key distinction to keep in mind for this question. But anyway, now that we've looked at the example, let's dive right into the question. Now, if you want to try this on your own, feel free to pause the video here and attempt to get the solution yourself. We're going to assume that you already tried that and came back. The first thing we're going to need to recall, of course, is what is a binary tree? Well, a binary tree is just a tree data structure where each node has at most 2 children. We're going to call them the left and right child, as per convention. And that's the only prerequisite that we need for this problem. So let's dive right into the intuition. Now, the first thing we need to notice about this problem is that to find a sequence of integers that equals a given sum when summed, another way we can do that is by taking the sum that we have and subtracting each member of the sequence and seeing if the final result is 0. And now we have to note that, of course, we only want to accept when we are 0 if we've reached every single member of the sequence. So another way to do that is to ensure that we only check after all members of the sequence have been subtracted from our number. Now, since the sequence has to be a root to leaf path, we need to use a traversal that will start at the root and work its way down, pathwise. So the first condition that we need here is that we need to start at the root and work our way down. That's going to knock out 2 traversals. So we cannot use here a post-order traversal, and we cannot use here a in-order traversal because those are not going to start from the root. On the other hand, since it needs to work its way down pathwise, as a depth-first search, we cannot use a level order traversal either, because that will use a breadth-first search. Therefore, it will break its paths apart as we try to traverse down the tree. Therefore, our only option left is to use the pre-order traversal on this tree. Now, once we've made this observation, the only thing we have to note is that we only need to do one path subtraction to evaluate to 0 in order to return true. That is, as long as one path is summing to our target value, we need to return true no matter what happens with all the other paths. Therefore, we can use the OR operator to string together our recursive calls and ensure that if any one call returns true, then the entire algorithm will return true. So we're going to combine pre-order traversal with the OR operator, and that's how we're going to evaluate whether or not this tree has a sum that is the target value. Okay, so let's do a quick example before we get into the algorithm. So let's do an intuition example here. Let's take a look at the same tree from up above. Now this tree is rooted at 5 with left child 4, right child 8, and so on. We already know that this should return true, but let's see the intuition in action. So as I said, we're going to do a pre-order traversal of this tree, which means we're going to start at the root 5. And we're going to move first leftwards. So again, in this depth first search, we're going to move leftwards until we reach the child, or the leaf node, before we start moving rightwards. So from 5, we move to 4, and from 4, we move to 11. And from 11, we move to 7. And all this time, we're subtracting each value from our sum. meaning that we get 22 minus 5 minus 4 minus 11 minus 7. And once we reached our leaf, it's time to evaluate whether or not this is equal to 0. Now, this is equal to 22 minus 11, giving us 11, minus another 9, giving us 2, minus 7, giving us negative 5. So this sum clearly does not evaluate to 22. Therefore, this root to leaf path is going to return false. So on our stack, we have a false. Or now we're going to evaluate the second path by popping off this member of the stack and moving rightwards. So we have false or, and now we look at the same path, 5, 4, 11. But now its fourth and final member is 2. Now we check, does this sum equal to 22? So 22 minus 11 gives us 11, minus 9 gives us 2, minus 2 gives us 0. So yes, in fact, this sequence does evaluate to 22. So now we're going to return true here, setting our new return equation to be false or true. Now, of course, we know that we can just return true here because we're using an OR operator, but let's continue tracing through the rest of this tree. So with a depth first search, we're now going to move right from the root as there's nothing right of 4, which means our next sequence is going to be 5, 8, 13. 5, 8, 13. Once again, does not sum to 22 as it sums to 26, so we're going to return false. And now we have false or true or false. Next, we're going to go back up and move rightwards down the tree, leaving us at 5, 8, 9, 1. Once again, this sum does not equal 22, so we're going to return false again here. Now notice that we did not return true more than once, even though there was another subsequence that summed to 22. Because as we said at the beginning, we don't want to consider the case where it's not a root to leaf path that does equal to 22. And now by using this depth first search that only terminates at the leaf node, we can ensure that we only evaluate root to leaf paths. So now that we've done an example of the intuition, let's actually take a look and try to build this algorithm. So our algorithm is going to start with the method header, taking 2 parameters. The node that is going to be the root of the tree, presumably, the root of whatever tree wants to be evaluated, and an integer, which we'll call num. Now this is going to be the sum that we want to reach. This algorithm is going to return a Boolean. So when we're writing these recursive algorithms, the first thing we need to consider is the base case. Now, the base case for this algorithm is going to be when our node is equal to null. In that case, there's nothing to evaluate here, so we're just going to now return whether or not our sum is equaling 0. Basically, that the number has been decreased by each value in the sequence and reached 0. So if we're at null, we're going to return num equals 0. But now we need to actually put these recursive calls onto the stack. So we're going to have a second return here. It's going to return 2 things. It's going to return one recursive call of path sum on node.left, and the second parameter being num minus node.data. So this is how we're going to emulate subtracting each member of the sequence. Then we're going to use the OR operator and concatenate this to path sum called on node.right, again, to mimic the preorder traversal, with second parameter num minus node.data. So as you'll notice here that once you reached the very bottom of a sequence or at the bottom of a path, so you've reached a leaf, this means that your next node, once you've moved left or right, is going to be null. At that point, you're going to return if that number that you pass into the second parameter is equal to 0. Because in each part of the stack, that number is going to be different based on which data has been subtracted from it. And all we need is that one of these situations occurs that the sequence returns 0 and returns true for the entire thing to return true by use of the OR operator. Now, the last thing to look at for this algorithm is its runtime. Now, since we are using a pre-order traversal here, the runtime, just like pre-order traversal, is going to be linear, or O of n. So that wraps up our discussion on path sum. If you found this tutorial useful, please leave a comment, like, and subscribe, share it with your friends. If you have a video done or any algorithm explained, you can also leave that in the comments and we'll definitely get to it. Otherwise, I hope you enjoyed this tutorial, and if you did, we'll see you in the next video.